Gulf of Coleraine is a place which, near Glasgow, which has huge waves and a whirlpool associated with the flood tide and the ebb tide. Now here we are. Here's Glasgow, and here's Jura, and here's Scarborough. And it's between them that you get this Gulf of Coleraine, the most dangerous place to sail around the UK. Here it is again, Scarborough, and here's Jura. And just want to remark, down here is Barn Hill. It's where George Orwell escaped after the war to write 1984. And he was with his young son, and they went sailing in this Gulf of Coleraine at the wrong time, and capsized and nearly came to grief. They were very lucky to be rescued. Anyway, because of the structure of the bottom, there's a pinnacle underneath. The interaction of the flood tide and the ebb tide with that causes huge whirlpools and huge standing waves. Away from this kilometre or so, a mile or so of this Gulf, it can be very calm. And I was there a few months ago. There are a few boatmen licensed to take tourists through this. They know what they're doing. You should never try to sail yourself. It's the world's third biggest whirlpool area. With our boat, what happened was that the pilot would see a whirlpool, they can usually 3 or 4 of them, and see a whirlpool, and sail into it, and turn off the engine, and you slowly go round and round, and a lovely thing. And huge standing waves, you can be 10 metres high. They weren't on the day that we went there, but it's kind of wild standing waves. Now, just one thing before I get back to the boat. We embarked on this tourist trip, place like north of Coleraine, and there were 2 boats, our boat and another boat from the same company, which had a television crew on it. And I got talking to a guy there who seemed to know all about tides, and I said to him, no, it's quite a dangerous place. George Orwell nearly came to grief with his young son. He said, yes, I do know. Have you George Orwell's son? He said, yes. We've been in correspondence. He was a retired engineer, slightly younger than me. He was too old at the time. He just about remembers it. But very often he lives somewhere in Warwickshire. He has a house up there. Occasionally takes groups of people and commentates about this tide of water. So it was kind of a very unexpected encounter. Now, every year I buy the tide tables from Victoria Arrowsmith Brown, whose company has been producing, his family have been producing the tide tables of the Bristol Channel since 1835. I've just received the other day the ones for next year. And this contains tides from navigationally interesting places of the Bristol Channel. And the northern place, the highest one upstream, in Sharpness, there it is. And look at the tides at Sharpness. And the tide at Sharpness is more than 9 metres high. Then there will be a bore higher up, it won't be 9 metres, it will be 1 or 2. But that's the algorithm, and then you can predict it. And it's very useful. Just a comment, the tides in the Bristol Channel, where the Avon and the Bristol News out into the Innsbruck, 2 bridges are the second highest in the world. So that's why this phenomenon happens. The tide range there can be 17 metres, a huge tide range. Okay, now there's a lovely book by the French surfer Anthony Collin called Masquerade on the Mer, which contains some lovely pictures, some of which I'm going to show you. Here's the Severn, actually. It's still turbulent, but you also see the undulations. Here are some people. By the way, it's much more magical to visit at night. There are fewer surfers, almost no surfers, and fewer boats. And there's always enough light from across the river, from the full moon, if it happens to be a full moon. And then the magical thing is that you hear the ball coming before you see it. You can't predict exactly when it's going to come. It's not like an eclipse. The reason is that when it comes, and how big it is, depends not only on the height of the tide, but on how much wind there is, how much water is in the river, what winds in the Atlantic, and so on. So you can predict about half an hour. And he's got a convenient table of if when the tide is high at Sharpness, when do you see the ball at different places? That's useful. There are a number of different places that they could visit. He also shows a picture of Amazon. Now, every year I visit an institute here, Physics Institute, and it's never quite at the right time to see this bird on a tributary of the Amazon. It's a very dramatic thing. It's called the Pororoca. There's some rather lovely pictures from him. You see the scale in there. To get there, it's not easy. You have to go to Berlin and you go 15 hours on the riverboat. It's a long... No, I've never done it. India, on the Hindu, there's the Ban. The Hindu is a distributor of the Ganges near Calcutta. And here we are. Here we see Calcutta. Here's the Hooghly coming down. And here's an old picture. This is where the Ban comes. Somebody has measured the profile. It doesn't always look like this. Sometimes you quite quickly get to something that's almost horizontal, which is the depth I called D1 before. I went to see it once, and it was actually not the best day out. We went over to the wrong place, the wrong side, and all we saw was that there was a gentle swiveling or rocking of the boats on the water. It was dramatic, as I'm going to show you now. Here we are. You see all the mud coming up. It's wedges all the mud from the riverbanks. Comes at about 10 or 12 miles an hour. I think a lot of fanciful picture. I don't know if the person who drew that ever actually seen it, but since I haven't seen it, it's best there, I can't really comment. But I want to read you something about the bow, this curve. The bow commences at Woodbury Point, the place where the river first contracts itself, and is perceptible above Woodbury town, and so quick is its motion that it hardly employs 4 hours in travelling from one to the other, though the distance is nearly 70 miles. At Calcutta, it sometimes occasions an instantaneous rise of 6 feet, and though further than every other part of its track, the boats on its approach immediately take the shore and make for safety to the middle of the river. In the channels between the islands of the Master of the Midnight, this height of the bow is said to exceed 12 feet, and is so terrific in its appearance and dangerous in its consequences that no boat will venture to pass at spring tide. I will read you this because of what he writes next. The river bore is fearsome as it could be, it is but a ripple compared to the Kiantang bore, the greatest of tidal bores. Between the river and the city walls, which are a mile distant, dense suburbs extend several miles along the banks. As the hour of flood tide approached, crowds gathered in the streets, running at right angles to the Kiantang, but at a safe distance. Now, I had the pleasure of visiting this Kiantang a few years ago, and I will tell you a little bit about it. So here it is. It's inland from Shanghai. Here's Shanghai. It's called the Silver Dragon, that tidal bore, and it's near the city of Hanguo, the historic and beautiful city of Hanguo. Now, just to give you an idea of the scale, where we see the bore on our river Seine, it's about 50 metres wide. Here, the bore is about 3 kilometres wide. Where our river Seine opens out into the Bristol Channel, it's very high tides and bridges are, it's a few kilometres across. Here, it's 40 kilometres across. A very dramatic, not quite the biggest bridge in the world, isn't it? Just recently opened, but it's very spectacular. There's a hotel in the early state, and every day we would take twice, 2 times a day, 3 days during this period of high tides to see the bore at slightly different places along the river. It's a local attraction. It's actually President Xi Jinping, quoted by the G20 speeches, and entertainers are there, clowns up and down, policemen. Why? Because some foolish people jumped into the bore, said they would kill it, it's actually dangerous. Many people are watching it. 120,000 was the estimate when we saw it. So here it is, we were in a cafe just above everybody, but we could see the bore beginning to come in. Here it comes by, there's a part of the turbulence there under the bore. And I want to show you this movie that I want to just make a comment. This will go out of shot. Now, when the bore is passed by, the water level is about this second story of this here you can see people standing at the scale. We can just see the far shore, far away, several kilometres distant. The transition is hugely landmarks right now. The table go upstream. It's very striking. I'll just show a picture that to the right. Just a comment. We stood in a place which we thought was good. And then suddenly a motorbike came and there were policemen screaming at us to go away, take a car. They were right, because where we were, the water had been killed. It had certainly been flooded, and the cars had been flooded to a depth higher than its wheels. So we were very grateful. So we stood somewhere else, which I took this picture from. We go out to focus and then come back again. This gives you an idea of the scale, because we by the way brought boats safely out of the way, so they did in the Kiantang River, and look at the size of the people where they are. Now I'm going to show you the rather beautiful wave effect that we saw there. Here's a little bit of the river, and the bore comes in, and part of it hits this jetty that's off, and there it is, and therefore can expect the reflection. Now I was aware of this because the first time I saw the bore, some of you may not know people who may know Ed Lorenz, who's from the pioneers of chaos theory. He didn't like to cut much from the route. He was persuaded to visit Bristol and give a talk, provided it was scheduled with a day when they would be bore. So we took him to see it on the second basis. And the highest point you can see is a place called Knavesmire. It's actually just the closest to Oxford. It's almost on the A40 line, so you can drive from here very easily. But just upstream of it is a pier which slices it. Before that pier was built, I think in the 30s, I'm not sure, about as far as Worcester. So we wondered if you would see a reflected bore. And sure enough, after about 15 minutes, we stand on the big lake, so before the river came down. Now I'll show you a more dramatic one. So here's the bore approaching, and then it hits the bore, you're standing on the bore, it's safe there, and then it interferes with its reflection. There it is, but this is a reflection travelling backwards, interfering with the bore travelling forwards. Very good. there are balls in France, several of them, and the Seine at Quebec. In French, where is Le Masquerade. That's the title of the book by Anthony Copparo, actually 2 books now. And there used to be a famous ball at Quebec. It no longer exists because they dredged the river to have navigation in that district. By the way, with the Seine ball, there's endless talk going back half a century about using the energy of the incoming outgoing tides to generate electricity with a tidal barrage, which of course kill the ball. Is that true? It's estimated that that would supply about 7% of the UK's electricity needs, which is pretty substantial. But of course, there are environmental considerations. It's built, so things almost never happen. Anyway, Quebec, here's some more pictures. There is a bar at Masquerade which you can visit, which we did, and we've seen pictures on the walls on the ball in those days. Here we are again. This is, again, I suspect a slightly fanciful picture from the popular astronomy book by Claude Flammarion, a famous astronomy book translated into English around the turn of the previous century, from which I want to read you 2 statements. One day, after being imprisoned at Quebec, after this always curious spectacle of the ball in the Seine, I returned on foot, where I was overtaken by a countryman, with whom I entered into conversation. On my asking him what he thought, and what the old people of his family thought, and of the phenomenon which they had observed for so many years, I do not know, he replied, how the wise men explain it. But for us, it seemed to be nothing else than the warring antipathy between salt water and fresh. They're not of the same character, you see, but this is certain, that the fresh water falling into the sea raises the salt water, with which it finds a difficulty in mixing. Really, the salt water ends by becoming angry, it accumulates its anger, and every evening, especially at equinoxes, when it's already naturally furious, it resolves on hunting the fresh water, sending it back with great velocity. I assure you, sir, that this reason is not simply in the attraction to me. I'm not reading this in a spirit, very contemptuous spirit, because, you know, if you don't have physics, you think of whatever you can in fresh water. It's a wrong theory, but still, you know, in physics, there are wrong theories which turn out to be very useful. Okay, so that's one. But now we're into another one, which goes back into mythology. The origin of the word Seine. The Seine, nymph of Ceres and daughter of Bacchus, looking one day on the seashore, was seen by Neptune, old monarch of the waters, who, delighted with her charms, set out to follow her. He really reached her, and Bacchus and Ceres, invoked by the nymph, being unable otherwise to save her, metamorphosed her into an azure river, which ever since has been her name, as everywhere on its banks joy and fertility. Neptune, however, has not ceased to love her, though she has preserved her aversion to him. Twice a day, he pursues her with great bellowing. This is the hardy Wallenstein of mythology. Each time, the Seine escapes into the meadows and goes back towards its source, contrary to the natural course of rivers. It's always interesting to see how natural phenomena are reflected in different cultures from the one we have now already introduced. Now, to finish. Well, what's the deepest reason to be interested in the ball? There are a number of reasons. I've described you various connection with quantum physics, with horizons and the like. But what is the most fundamental aspect of the goal of physics? It's unification. Now, unification is connecting unexpected things. And everyone is familiar with Maxwell's unification of the middle of the 19th century, where he showed that electricity and magnetism and light are all part of the same phenomenon, a great unification. Now, of course, we try to unify gravity and other forces and so on. It's easy to forget that the first unification was Isaac Newton's, who told us that gravity that holds us down and holds the earth in its orbit and the moon that pulls the tides is the same force. This was a fantastic discovery and a great unification. And when you see this tidal ball, before your eyes, you're seeing this unification of because the tides are pulled by the moon, whose orbit, of course, is determined by gravity, and the water is held down by the same earth which holds us down. So really, this unification becomes immediate. So it's a really lovely thing to see and contemplate. This in 2 papers. One, before I made the theory, there's a little travelogue about the Silver Dragon visit, and then there's the theory, which was published earlier this year. The first of these is in my book, which has at least 1 reader. Thank you.
I'd also like to add my thanks for hosting us here in Solihull and to say hi to everyone else in the universe there. I think we as humans spend a lot of our time thinking about the future. I did an exercise with the BBC where we were doing a program about consciousness, and I think it's one of the unique kind of traits of consciousness that it allows us to imagine ourselves into the future. I have a cat at home, and my cat just sits there enjoying the day. I don't think it spends very much time thinking about what's going to happen next. But actually, one of the best tools we've developed to enable us to try and look into the future and make predictions, I think is our subject of mathematics. Actually, it's very curious. When I'm at a party and somebody asks me, oh, what do you do? And I say I'm a mathematicician. I don't know whether you find this out, but there's this kind of look of horror appears on the person's face, and they back away, sort of the glass becomes very empty very quickly. And actually, before they go, they always seem to tell me what they got in their GCSE or O-level. I'm not sure what that's about. But anyway, I'm a mathematician. I chase after them. I began to realise that mathematicians were a very misunderstood breed. I think most people think, well, what are we doing in our offices in Oxford all day as mathematicians? And as I talk to people, I've got this feeling that they think I'm doing long division to a lot of decimal places, and surely my computer has put me out of a job by now. But I try to explain to them that, no, actually, mathematics, if I was going to define mathematics, I would define it as the science of pattern searching. And it's that ability to understand a pattern which gives us this great tool to be able to look into the future. Because by looking at a pattern, say, of data in the past, if we can find that pattern, then we might be able to read that pattern so we can predict what it's going to do in the future. How do we know about what the trajectory of our universe is? Because we've seen the data of the universe from the telescopes that we've... and it's amazing, we're stuck on this planet, yet through the information we've got, we're able to see that we can work our way backwards to see we came from a Big Bang, and forwards to see what will happen to the universe in the future. Even on our sort of more local scale of the universe, by looking at the data of the climate, we're beginning to understand what might be happening in the future, and we're going to have to use our science and mathematics to actually do something about what that trajectory looks like. So I think for me, mathematics is all about looking for patterns. So what I would love to do in this presentation is to show you some of the power of mathematics to predict things, but also some of the limitations. That mathematics can't let us know everything about the future. I think that the challenge of pattern searching, for me, is kind of perfectly encapsulated in the challenge you've probably had at school, where you're given a sequence of numbers, and you have to try and spot what's the logic behind the sequence of numbers to be able to tell what's going to happen next. So I thought I'd see how good you are here in Solihull at predicting what's going to happen next. So I've got a series of challenges for you, which gets a little bit more difficult as we go on. So a sequence of numbers, what I want you to do is, can you work out what the pattern is, and be able to predict what's going to happen next. So we'll start with a very easy one. 1, 3, 6, 10, 15, 21, 28. What's the next number in that sequence? 36, very easy. So how do we get 36? Yeah, I'm pointing at you. You seem very loud and...
Yeah, between the first two is 2, the 3, 4, and so on.
Exactly. You're sort of adding one more number on each time. 1 plus 2 plus 3 plus 4. In fact, we call these the triangular numbers because you can view them very geometrically. It's the number of stones you need to make a triangle, how many stones you need when you add on an extra layer each time. And actually, if you want to know, for example, what the 100th triangular number is, so how would you know way into the future what this number, the sequence is going to do? Well, you could do the kind of, the dull way would be add up all the numbers from 1 to 100, but mathematicians were not very good at kind of arithmetic, actually, so I'd probably make a mistake if I did that. But what we want is kind of to understand maybe a formula which will tell us a smart way to understand what the 100th number might be. And here's a trick I often use in my own research, which is kind of changing the language. So instead of considering numbers, to get this formula, if you consider these things more geometrically, here's some triangles. If I put 2 triangles together, I get a rectangle. Well, counting things in a rectangle is easy because it's the base times the height. So I can calculate the number of stones there. A triangle, I just halve that number, and then I have a formula which will tell me the 100th, the 1000th, any number in this sequence. So this is a sequence we understand very well. Okay, well, if you've read the Da Vinci Code, you're not allowed to play on this one because this is the one of the challenges, first challenges Dan Brown sets you in the Da Vinci Code. So what's the number in this sequence? 1, 1, 2, 3, 5, 8, 13, 21. 34, okay, very famous sequence. You got that by adding the 2 previous numbers together. So these are called the Fibonacci numbers, named after this Italian mathematician of the 12th, 13th century, who understood that these are nature's favourite numbers. You find them all over the natural world. So, for example, if you cut a fruit open, an apple sort of horizontally, you find a 5-pointed star inside. Or a banana, you'll find a 3-pointed star. A charon fruit, an 8-pointed star. Pineapples, you'll find these numbers spiraling up and down. Flowers, if you count the number of petals on a flower, invariably it's a number in the Fibonacci sequence. And if it isn't a number in the Fibonacci sequence, that's because a petal has fallen off your flower, which is how mathematicians get around exceptions. So actually, these numbers shouldn't be called the Fibonacci numbers. I discovered quite recently that they were discovered before Fibonacci ever found them in nature, not by mathematicians, but by Indian musicians and poets who understood that these numbers also help you to count the number of rhythms that are possible if you're a tabla player, that you can make out of long and short beats. So one of the things you find mathematics all over the place, not just nature, but also in the world of art as well. Now this sequence, we haven't known quite a lot about this sequence. We have a formula, again, which will calculate the 100th Fibonacci number without having to add all the pairs all the way up to 100. It's a bit more complicated than the triangular numbers. It involves this wonderful number, the golden ratio. You have to take powers of the golden ratio. But there's a lot of mysteries we still don't know about these numbers. So there's still some things, number mysteries to solve about the Fibonacci numbers. Okay, the next sequence. 1, 2, 4, 8, 16. 32 is a possible answer, but 31 is also an equally valid answer to this sequence. You thought, okay, this is just doubling. 32 seems to be the most obvious. But why, if anyone shouted out 31, would that be equally correct? Well, these numbers up to 16 are actually counting something called the circle division numbers. So what are these? If I take a circle and I took 1 point in that circle, now I've just got 1 region of the circle in the middle. But now let's put another point and join these 2 points up. Well, now I've got 2 regions. So let's keep on going. We'll add another point, join up all the lines. I've got a triangle in the middle, 3 regions around the outside. That's 4 regions. Okay, so you think, okay, well, so I want to spot the pattern here. Add a point, another one. We join all of the 4 points up. Well, it's a nice little envelope in the middle. 4 triangles there. 4 regions around the outside. 8. You keep going. What about 5? Sure enough, you get this lovely 5-pointed star, pentagon. 16. And by now you think, oh, it's pretty obvious. Every time you add a point, you somehow double up the number of regions. And so you make a conjecture that the pattern is going to go in this direction, just double. And then you get a surprise, because when you put 6 dots on the circle and join those up, the largest number of regions you can get is 31. So for really this is quite one of the excitements of mathematics, because there are often kind of surprises out there, unexpected directions that something can go in. So there is a formula for the number of regions. It's not doubling. It's a slightly more complicated formula. This is quartic polynomial, where you raise the number of points on the circle to the power 4 and do a further calculation. But this formula tells us how this number of regions grows. It grows much slower than just doubling. And this might be a practical problem where you've actually got some sort of network and you need to know how many regions this can be divided up into. So you're going to need to know how this pattern emerges, or you won't have quite as many as you think if it's just simply doubling. So another warning here, see, that a pattern might be starting to grow, but suddenly the thing can go off in a completely new direction. So you have to be prepared for surprises in mathematics, which is one of the reasons it's so much fun anyway. Okay, so a little bit more. That spoils my. Okay, so if everybody saw quite what popped up there, a little bit more challenging sequence. 2, 9, 10, 11, 13, 16. Usually this has the mathematicians really working hard because they see some sequence going here. But as I flashed up rather too quickly there, these don't have any pattern at all, because these are in fact the National Lottery winning numbers for the 28th of September. So another warning here that not everything has a pattern to it. So you have to pick your battles carefully when you're looking at data. And quite often there can be things that you think are patterns, but which actually just the result of kind of randomness, and the pattern can kind of just disappear. But in a little bit I'll show you that even when something is as random as the National Lottery, mathematics has tools to be able to make quite powerful predictions about even things which are genuinely random. Okay, what about the last sequence? 2, 3, 5, 7, 11, 13, 17, 19.